right. Well, I should be pretty good at this one by now because I made an entire recording of it and then it didn't upload. So that was a huge bummer. All right. That's not your problem though. That's just me being bitter. All right. So let's talk today about independent and dependent events. I encourage you to obviously listen and take notes on this, but to also have out with you while we're doing this, the optional assignment, which is 10-7 practice C. This is going to look a lot like some of your probability questions on Delta Math this week. And so I'm actually going to do that entire worksheet with you guys. So should have that out if you can. If you need to pause it, go ahead. Okay. So this idea of independent and dependent events is like when you have, more than one probability that you have to find. Like, what's the probability of you picking 2 marbles out of a jar that are both red? What's the probability of you picking 1 red marble and then 1 green marble? What's the probability of you rolling a 5 and then rolling a 6 on dice, right? So we talk about these, like what we've been doing this whole week has been just simple probabilities, like the probability of one event. So this takes more than one event and puts it together. So in order for us to do that successfully, we have to understand the difference between these two things, which are independent events and dependent events. So independent events is when the probability of one outcome, outcome A, I guess you could say, outcome A, let's do that. Probability of outcome A has no effect on the probability of outcome B. Okay, that's independent events. Dependent events is the opposite. It is when the probability or the outcome, I should say, of A does, in fact, have an effect on the probability of outcome B. And you might think, well, why would those be different? Like, why would it sometimes have an effect and why would it sometimes not? Well, take a look at these up here, these book titles, right? So if your teacher, I have Mrs. McLaughlin here, she's my friend. So if she tells you to pick 2 books to read, you have this option 1 and option 2 here. So your option 1 is one title from each of these lists, right? So I have Animal Farm and Ethan Frome and Frankenstein and Great Expectations and Jane Eyre. And then I have a separate list of Never Cry Wolf, Night, Things Fall Apart, Wish You Well, and Wuthering Heights. So if I want, I can pick Animal Farm from list 1. And I can pick Wuthering Heights from list 2. But if I look over here at option 2, I have to pick 2 titles from the same list. Because if you look at this, it's the same, like this is Animal Farm, Ethan Frome, Frankenstein, Great Expectations, and Jane Eyre. Also, Animal Farm, Ethan Frome, Frankenstein, Great Expectations, and Jane Eyre. So the fact that these are the same titles means that if I pick Animal Farm here, I can't pick it again. Here I have to pick Frankenstein. So what happens is once I pick this, it's taken out. So now I had 1, 2, 3, 4, 5 choices in the first one, but now I only have 1, 2, 3, 4. So your denominators here have changed, right? So if I have to pick 2 titles from the same list, I have like a 1 in 5 chance here picking Animal Farm, and I have a 1 in 4 picking Frankenstein. Whereas from this list, I have 5 choices here, and I still have 5 choices over here. So my items changed, my denominator did not change. So probability, independent events, probability of one outcome has no effect on the probability of outcome B. So the chance of me picking Animal Farm here or me picking Animal Farm here has no effect on whether I pick Wuthering Heights here. So this is my independent event. Over here, me picking Animal Farm in the first one absolutely has an effect on what I can pick here because now I don't have Animal Farm to pick again. So this is my dependent event. Okay, so what I guess dependent, right? What I can pick here depends on what I did here. So that's sort of what we're looking at with probability, right? So you're dependent if what you do in this, what happens in the second event is dependent on what happened in the first. Okay. All right, so we're going to tell whether each set of events is independent or dependent and explain. So I'm going to select a card from my standard deck of cards and hold it. This is important, okay? A friend selects another card from the same deck. Here are my cards again, right? So if I say, hey, friend, pick a card, any card you want, and they say, okay, I want this one, and it's a Jack of Clubs, and then I say, okay, friend, pick the card, any card you want. They don't have the option to pick the Jack of Clubs anymore, right? So they started with 52 cards, and now because the Jack of Clubs is still sitting here, there's just 51. So that does change what I can do in the second one because I can't pick the Jack of Clubs anymore. So if I pick that one, Queen of Diamonds, whatever. Okay. So we're going to say that this is dependent. Again, because the fact that I'm still hanging onto that card means that I didn't I created new stakes for the game, so to speak. All right, I flip a coin and it lands heads up. Ooh, where's my quarter? I thought it was here. Oh, I think it's in my pocket. And then I flip the same coin and it lands heads up again. Okay, so if I flip this, we're going to pick heads up. Yay. Right? And then I'm going to flip it again. Well, because I landed heads last time, does that have anything to do with whether I'm going to land on heads this time? Absolutely not. So these are independent events. Again, remember, like independent means the first event or outcome has no effect on what the outcome can be the second time. Like your probability of flipping heads does not change because you did it the first time. All right, a number cube, remember those are dice, lands showing an odd number. Here we go. Then it's rolled a second time and it lands showing a 6. There's my 6. Did the fact that I landed on a 3 the first time have any effect on the second roll? No. So again, that's independent. One student in your class is chosen for a project. Then another student in the class is chosen. Okay, well, let's say I have 26 kids in the class, right? So if I pick one, how many do I have left? 25. So I can't pick. Let's say I picked a kid named Bobby. Okay, he's pick 1. I can't pick Bobby the second time because I already did. So it's the same kind of thing as this in part A, picking the cards and holding it. You're changing the denominator. So just for fun, let's see if we can figure out the probability of this or how we would write it. So my first pick, if my chances of picking Bobby are 1 out of 26, right? Now my second pick, my chances of picking any other random student, because can't pick Bobby, are now 1 out of how many kids are left? 25. And what we're going to do with these two probabilities is the subject of the rest of this lesson. Okay. So we have to, before we do anything else, or before you figure out probabilities of this, you have to figure out whether you're dealing with independent or dependent events every time. Okay. Now, these are not super different formulas. Okay. So this isn't for independent. This is dependent. Remember, P and then parentheses means the probability of whatever. So probability of A and B happening if they're independent events, meaning that the outcome of A does not affect probability of B. Okay. So doesn't, does not, doesn't. Then I simply take the two probabilities and I multiply them together. Okay, the probability of, flipping a coin, landing on heads, and then, rolling a dice and landing on a 4, right? So And then probability independent, so probability of A and B, you're still multiplying them, but you multiply, so the probability of A, so probability of the first event, times the probability of B after A. Sometimes this is written as B given A. And what that means is you assume that A happened, right? So let's say I want to know what the probability was of me, pulling a king of spades out from a deck of cards, holding on to it, and then getting a two of diamonds, right? So I assume that I pulled the king of spades first. And then I go for the probability of the, I don't even, ace of diamonds, two of diamonds, whatever I said, after the fact that I already pulled that first one. All right, it'll make more sense when we do the math behind it. All right, flipping two different coins and each coin landing showing heads. So first we have to decide whether it's independent or dependent. Well, I have two coins, and this second one does not depend on what happened on the first one, right? So it's the probability of A and B, in this case, H, so both heads, equals the probability of heads times the probability of heads, because both of them need to land showing heads. So probability of heads is 1/2. This probability of heads, still 1/2. So probability of heads and heads, I take 1/2 times 1/2. And remember, when you're multiplying fractions, multiply the top. So 1 times 1 is 1. 2 times 2 is 4. Make sure that it's reduced to lowest terms, as always. And there you go. And you can put it as a decimal or a percent too, remember. In this instance, it's usually easiest to leave it as a fraction in lowest terms. But again, like I said before, always just go with what the question asks you. All right, number 2, drawing a red card from a standard deck of cards and not replacing it. Then draw a black card from the same deck of cards. Okay, here is your clue, whether it is independent or dependent. If I do not replace something, I don't put a card back in a deck, I don't put a marble back in a bag of marbles, etc., it is a dependent event. Now, there's other times that can be dependent that don't have to do with replacement necessarily, but literally every single time you don't replace something, then it's a dependent event. All right, so drawing a red card. So this is the first, so that's my A. Not replacing it, then drawing a black card, so that's B. So remember, we have to remember how our cards work, right? So we have 52 total cards, and there's 26 red, 26 black, right? Okay, so probability of red and black is the probability of red times the probability of black after or given red, right? Because it's a dependent event, so we have to use this formula up here. So the probability of red is 26 over 52, right? Because half of my cards are red. So there you go. Now, this is the tricky one. The probability of black given red, I have 26 black cards. I have not taken any of those. However, if I drew my red card and I did not replace that, my denominator changes. I no longer have 52 cards. I have 51. So now I'm going to multiply 26 over 52 times 26 over 51. Might be a little bit easier to reduce one of these first. I mean, you can use a calculator too, but that's 1/2, right? So now we do 1 times 26 is 26. 2 times 51 is 102. And then you could reduce from there as well. So 2 goes into both of the, sorry, I got distracted for a second. So 2 goes into both of those. And then if you want it in lowest terms, you just put 13 over 51. All right. So this one, number 3, is a little bit tricky because it actually gives it to you in a different order, so you have to be careful. Probability of drawing an ace after you've drawn a king and put the king back in the deck. So after I've drawn the king, so to draw a king, that's my A. Drawing an ace after that, that's my B. I put it back in the deck, so I replaced it. If I replace, that means it's independent. Because remember, not replacing is dependent, replacing is independent. Because it just doesn't, like, it doesn't make any difference, right? So if I, like, pick any card out of here, and I say, oh, I have the ace of hearts. Oh, what a lovely ace of hearts that is. And I put it back, still have all the same cards in the same deck, right? So that's the independent part of this. All right, so probability of king and ace equals probability of king times probability of ace. Now, don't write ace given king because this is independent. Well, my probability of a king, I have 4 kings, right? Because remember, I have 4 suits. I have hearts, diamonds, clubs, and spades. And I have 2 through 10, jack, queen, king, ace of each one of those. So I have the king of hearts, the king of diamonds, the king of spades, the king of clubs. So I have 4 kings out of 52 cards. And then an ace, I also have 4 of out of 52. So I multiply these together. Again, I would suggest reducing these first, especially if you're not using a calculator. So 4 out of 52 is 1 out of 13, both times. So 1 times 1 is 1. 13 times 13 is 169. You should expect a lot of these to be like kind of larger denominators. All right, the probability that you will roll a 5 on a standard die and then get tails when you flip a coin. Okay, well, are these independent or are they dependent? Does rolling a 5 have anything to do with flipping a coin? It does not. So this is independent. So probability of, let's see, I'll roll a 5. That's A. Then get tails. That's B. So probability of 5 and tails equals the probability of a 5 times the probability of tails. Probability of a 5 is there's 1 5, 6 sides on a die, so it's 1 out of 6. Probability of tails is 1 side is tails out of a 2-sided coin. So this is, let's see, probability of 5 A and T is 1 6 times 1 half, which is 1 12. All right, so those are pretty easy. The ones that are in Delta Math are a little bit strange because some of them are tables, like two-way tables. So that's why I'm going to go ahead and I'm going to do like this entire sheet just so we can kind of really super practice this because it does, it's sometimes a little bit confusing. All right, so remember, you have this out, like I said in the beginning. All right, so 1 and 2, I'm just supposed to tell whether each set of events is independent or dependent. All right, so I'm selecting 3 marbles at the same time. So we're assuming like from a bag of marbles, right? So remember how I said like replacing and not replacing? Well, it's kind of sneaky sometimes. Sorry to move that, was bothering me. Whether you're replacing or not replacing. Words like at the same time would suggest that you're not replacing. So I'm not going to like pick a marble out and then say, oh, what a pretty marble, and then put it back and then pick another one and, oh, what a pretty marble, and put it back. I'm taking 1, 2, 3, not putting them back in there. So this is a dependent event. And the explanation could just simply be you're not replacing, but it could also be that the number of marbles to choose from every time changes. And that's a good indicator too of dependent events. So dependent events, remember, so we either have like not replacing, but also if you're looking at mathematically, usually your denominator changes. Sometimes your numerator changes as well. And that's like, when I say denominator changes, I mean of the same event, right? Because like your denominator is different in independent events sometimes too. So you're talking about like flipping a coin and rolling a dice. Those have two different denominators. One is a denominator of 2, one's a denominator of 6. That's not changing though. What I mean is like from the same event, or from the same event, your denominator changes. So your cards go down from 52 to 51. Your marbles go from 10 to 9 to 8 to 7. Okay. Sorry. All right. You guess the answers on a multiple choice test. Well, as much as you guys think that we put all this thought into the order of our answers and stuff, that is not true. So the answer to question 1 does not give any indication to the answer of question 2, right? So guessing the answers on multiple choice tests is an independent event. And simply put, the answers don't have anything to do with each other for the most part. And I'm sure that some of you guys are like, but what if it's like a series of questions? And okay, fine. But in terms of whether the answer is A, B, C, or D, that is what I mean by it. That doesn't matter. The actual answer itself might be indicated somehow in a previous answer, but not the letter choice. Okay. Now the rest of these I have to actually find the probability. So a music player has 10 songs. The songs are played on the player randomly. What is the probability that your favorite song will be played twice in a row? Okay. Well, if these are played randomly, then that means that I can have songs that come up the same song come up again, right? If it's just like an old record player, a CD or a tape player, something like that, where the songs just play in order, and unless you do something to actively skip or go back, they're not going to play in order, or I'm sorry, randomly or again. So this would be an independent event. So my probability of my favorite song twice in a row is probability of favorite and favorite is the probability of my favorite times the probability of my favorite. Probability of my favorite song happening once out of 10 is 1/10. Probability of it happening again, because they're independent events, it doesn't change. It's not like the song goes away, right? So it's just 1/10 times 1/10. 1 times 1 is 1. 10 times 10 is 100. All right, a coin is tossed 4 times. What is the probability of getting 4 tails? Again, each coin toss does not indicate what's going to happen in the next one. So these are also independent events. So I want the probability of just kidding, tails. Sorry. Probability of tails, 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 and tails. Well, the probability of tails once is 1/2. Twice is also 1/2, also 1/2, and also 1/2. Because again, you don't change the coin or the weight of the coin or anything like that based on what happened last time. 1 times 1 times 1 times 1 is still 1. 2 times 2 times 2 times 2, or 2 to the 4th, however you want to write it, is 16. So this is 1/16. What is the probability, number 5, of selecting 4 cards from a random deck and getting all 4 aces? Okay, here's the other thing here. It does not say you're replacing it. When it doesn't say either way, you assume that you are not replacing. Okay, the replacing thing is the kind of thing that they'll tell you. So what you're looking for here is the probability of ace and an ace and an ace and an ace. And this is going to be a crazy one, right? Because you have to assume it's probability of ace 1 times the probability of ace 2, given that you got ace 1, times the probability of ace 3, given that you got ace 2 and ace 1, etc. Okay, you don't have to write all that out. All right, so the probability of getting an ace. We have 4 aces. We have 52 total cards. So the probability of the first ace is simply 4/52. Now, and this is where I said on the note sheet, you have to assume that your desired outcome happened. So you assume that you got that first ace. If that is true, how many aces do I have left? Well, I have 3. How many total cards? 51. That third ace, I got ace 1 and ace 2. So now I only have 2 aces left, and I have 50 cards. And then now I only have 1 ace left, and I have 49 cards. This is one where if you like multiply it together as fractions, you'll get a scientific notation answer, which will not be super fun. So in this instance, I would suggest to you you could reduce first if you want to, or to just simply multiply the numerators and get something, multiply the denominators and get something, and put that as a fraction over each other. So, but actually, let's reduce. So that's 1, that's 13, that's 1, that's 17, that's 1, that's 25, and then 49 doesn't reduce. So 1, 1, 1, 1 is 1. And now I just have to multiply 13 times 17 times 25 times 49. Times 45 times 49. I almost put 79 in my calculator. That would have been wrong. So 1 over 270,725. So if you do that, what this is saying is like, this is difficult to do. So if you do it, you should be very impressed with yourself, right? All right, so that's the answer for that one. Okay, now 6 says there are 10 pens in a desk. 2 of them have no ink. That's a bummer, but it also sounds like my desk. Okay, the pen is randomly selected and replaced. So what does that tell you first? This is dependent. Then a pen is selected again. What's the probability of both selections? I'm sorry. That's not, I'm sorry, I said replaced and that was dependent and I didn't mean that. So replace is independent. Then a pen is selected again. What is the probability both selections will be a pen with no ink? Okay, so probability of no ink and no ink, but with replacement. So, which is the probability of no ink times the probability of no ink. Probability of no ink is 2 out of 10 because 2 pens have no ink, 10 total pens. Then remember, I put it back. So I picked it and I had no ink and I'm like, well, that's stupid. I need ink. And so I put it back, which is also dumb because like, why would I do that? Because I could pick it again. But anyway, if I put it back, I still have 2 pens with no ink and I still have 10 total pens. So this is 1/5, 1/5. So 1 times 1 is 1, 5 times 5 is 25. Now, part B, a pen is selected and not replaced. So this is dependent. What's the probability that both pens have no ink? Okay, this you should expect like a smaller probability or a larger denominator, because when you're not replacing it, then you have less chances to pick it, right? So the first time, so a pen with no ink and no ink is the probability of no ink times the probability of no ink given no ink. So probability of no ink the first time is 2 over 10. Now I have gotten one of my no ink pens. I did not put it back. So I only have 1 left out of 9 total pens, right? So I can do reduce here. So 1 times 1 is 1. 5 times 9 is 45. So you have a greater chance of pulling it twice if you put it back. You have a smaller chance of doing it if you don't put it back. All right, number 7. A bag contains 5 yellow, 8 red, and 2 green marbles. First of all, anytime you see something like this, you're going to want to add all of these up. So 8 plus 2 is 10, plus 5 is 15. So I have 15 total. That's always good information to have before you get started. What is our probability of selecting 1 yellow marble, replacing it, so that's independent, then selecting another yellow marble? So what's the probability of getting yellow and yellow? With replacement, it's just the probability of yellow times itself, right? So yellow, I have 5 yellow over 15 marbles total. And then I'm putting it back, so I still have 5 yellow and I still have 15 marbles. And again, if you want to reduce, these are both 1/3. So So you get 1/9. All right. What is the probability of selecting 3 red marbles without replacement? So that is dependent. So I need 3 red in a row. Okay. So the probability of red, just red, is 8/15, right? So my first one is 8/15. And I'm like, yeah, I got my red marble. I didn't replace it. I want to try to pick another one. There are 7 red marbles left, 14 total marbles. And I got my second. I'm like, yeah, I'm so excited. I got to go for a third. And then I have 6 red marbles left that I could possibly pick, 13 total marbles in the bag. So this is one, again, you're going to want your calculator for. So 8 times 7 times 6. So my top is 336. 15 times 14 times 13 is 2,730. And then if I do 336 divided by 2730, then hit math, enter, enter, I get 8/65. All right, what's the probability of selecting a red and yellow marble without replacement? Without replacement, that means it's dependent. So I'm going to pick my red first. So if I want red and yellow, it'll be probability of red times the probability of yellow, given that I picked red. Sorry, I didn't mean to do those in the wrong order and confuse you. All right, so I have 8 red over 15. That's my red. Now I want yellow. I have 5 yellow because I still have all my total yellows. What I don't have is my total marbles. Haha, right? Lost my marbles. All right. So that goes down by 1, so I have 14. So 8 times 5 is 40. 15 times 14 is 210. And then if you just lop that 0 off each, you have 4/21. Okay. So looking at these tables now, this is what some of your Delta Math stuff is going to be, is like this tables. So you have to look and see what you want from these. So table shows the failure rates in decimals for 3 products. Assume all failures are independent. It's good information to have. Find each probability as a percent. As a percent, so these are not given as percents right now, they're given as decimals. So we'll have to move the decimal to the right every time, right? All right. So for 8, so product A has an assembly error and a manufacturing defect. Okay, well, it's just probability of an assembly error and a defect. So the probability of an assembly error is 0.02. These are my real small numbers we're working with. And then manufacturing defect, it's 0.001. So when you do this, ooh, that's a glare, sorry. 0.02 times 0.001. Oops. I think, because I just randomly added in a parentheses in there. So 0.02 times 0.001. All right, so this 2e negative 5, you're like, what the heck is that? This is 2 times 10 to the negative 5th. Ooh, what did that mean? That was scientific notation. Remember? So 2 times 10 to the negative 5th means there's a decimal place here at the end of 2. And then negative 5 means I move it 5 places to the left. So 1, 2, 3, 4, 5. Put a decimal. I fill in all of this with zeros. So it's 0.0002. However, oops, I missed one. There. 0.00002. But I need it as a percent. So I have to move it back over 2. So this will be 0.002%. B has a design error. So B here has a design error and an assembly error. So P of design error and assembly error. So design error is 0.012 and then assembly error is 0.01. So 0.012 times 0.01 is, again, I have this 1.2 times e to the negative 4. So it's 1.2, but e negative 4. So 1, 2, 3, 4. So I have 3 zeros in front, so it's 0.00012. But again, I need as a percent to move it 2 over. So I have 0.012%. The other thing you could have done, since this is e negative 4, and you know you're going to have to move it back 2 to the right, you could just do you could do times 10 to the negative 2 first, and then save yourself that hassle, but whatever you choose to do. All right, A and C have improper material. So A, improper material, and C, improper material. So probability of A and C having improper material is 0.06 times 0.023. So I have 0.00138, and again, if I move it over, it's 0.138%. All right, so hopefully, it's a lot more math, and it does get a little bit confusing sometimes. So hopefully that helps a little bit, and you can work that out with your Delta Math. If not, certainly email me, hit me up on Zoom. If you're going to do that, remember to take a screenshot if you're on Delta Math, so I can see exactly which problem you're looking at, and then email that to me. All right, that is it for the week. Goodbye. I say goodbye. I haven't left yet because I still need to figure out how to stop this.